galactic plane surveys and what we will learn from this. So Oleg, go ahead.
Thank you very much. So my main goal is to sort of supplement Arash's talk and talk a little bit about what will be needed to take full advantage of the products from the Galactic Plane Survey, and also to talk a little bit about what this survey may not do, but it is still important to do it either through additional guaranteed time program or as a guest investigator. That's something to decide. So the talk is kind of two parts. One part is about the interpretation of the results of the Galactic Plane Survey, and the other part of the talk is about high energy extended or diffuse sources in the GPS area and overall in the wider galactic plane. So this is the picture, which is like similar to what Arash was showing. It shows the area of covered by the survey, by the GPS, Axis GPS. And Axis GPS is focusing on the faint X-ray sources. That's really like the point that Arash was stressing, because we don't really understand the lower luminosity end of the luminosity function for X-ray sources. And Axis will be discovering many of those sources. And we are targeting a very densely populated region of the galactic plane. So that means actually that any meaningful study of the sources detected in the GPS, and one can think immediately about the population studies, right? For example, we will discover, many maybe quiescent X-ray binaries, faint cataclysmic variables, and so on. But you have to assign an astrophysical class to those objects to do a population study, right? To be able to understand the physics behind. And therefore, this classification, understanding whether it is a faint CV or Black Widow type pulsar, or is it, other kind of accreting at low rate X-ray binary, this is important work that will need to be done. Now, this is actually quite challenging for two reasons. First, it's densely populated regions, so one has to be able to assign multi-wavelength counterparts in order to be able to do successful classifications of faint X-ray sources, right? Because if your X-ray source is bright and you have a lot of photons, maybe you can see iron line complex or something like that, and that allows you, or pulsations, and you can classify your source. But most of these sources in the GPS area will not have huge amount of X-ray photons detected. And therefore, multi-wavelength information is very important to be able to do the classifications. But for that, you actually need to be able to assign those multi-wavelength counterparts. And this will be a challenge. I'll illustrate it later in the slide, because it is a densely populated region. The other challenge is that if you have a lot of sources and actually multiple possible multi-wavelength counterparts to each X-ray source, and Arash demonstrated that we will have hundreds of thousands of X-ray sources. So one would have to take some kind of automated approach to classification. And it's better be some probabilistic approach where you can assign, one can assign the class probability, because it's obviously is not going to be 100%. And recently there were these efforts, and I'm part of one of those efforts, to do what's called machine learning classification of X-ray sources. On the left-hand side, you can see work done by European group for the XMM and Swift catalogs, and on the right-hand side is our work with MAV class pipeline that we developed in our group. This was focusing on Chandra source catalog. And it is a recent paper by Hui Yang, who is here in the audience, led by Hui Yang. So the important things to understand is that we would need to have multi-wavelength information. You can see it in this feature importance plot, which at the bottom has X-ray information, like hardness ratios that we need to measure with Axis, fluxes in multiple bands, variability, but then there's a lot of multi-wavelength information. And with that in hand, we should be able to perform classifications of a large fraction of sources if we are able to identify multi-wavelength counterparts. So here is on the left-hand side is an example of how axis image of some dense region in the galactic plane might look like on the left at the top, or the Westerlund 1 cluster, let's say. Here, so there's many sources, but if you actually look at the deep near-infrared survey, and it has to be near-infrared because these are pretty absorbed areas of the galactic plane, but Arash mentioned that we have those near-infrared deep surveys already, and actually there's some coming up that will be available, even better surveys. So you see a lot of near-infrared sources. That's the middle panel in this slide. And the right-hand side panel is showing the same area of the sky in X-rays as in the middle panel. Middle is infrared and right is X-rays with Chandra. So axis hopefully will be a comparable quality to this Chandra image that is a bit beamed up, maybe by a factor of 2. And so, but still, you see, there could be multiple sources there. For example, the circles show typical XMM uncertainty and typical Chandra uncertainty, and axis hopefully will not be too much worse than Chandra. Of course, the resolution, the point spread function may be, maybe 1 arcsecond instead of 0.5, but maybe we will collect more counts, which helps with centroiding and uncertainty and so on. But this is just one thing that everyone should be aware. Even if we are going after point sources and X-rays, understanding their nature still requires excellent resolution in these dense areas of the galactic plane. Therefore, it is important to maintain as good as possible resolution for axis so that we can reduce the number of possible multi-wavelength counterparts. This is just like some plots from our current efforts to perform this multi-wavelength classification with Chandra. As you can see, different classes of X-ray sources shown by different colors here. They kind of cluster nicely in different areas of this feature space if multiple features are used, which shows that the classification is actually possible. You can look up and play with these plots at that website. So these are the classes that I currently have in our training data set. This is a supervised learning approach to classification, so where you actually collect very well confidently determined sources from different classes in the training data set, and these plots are showing the training data set. You can see the content in the table. And so far, the performance, for some classes is very good. The machine learning pipeline is able to classify confidently. For some, is not so good. We are working on improving it, and Yang may talk later, next year about the latest improvements. Now, I'd like to talk a little bit about the second part here is about extended high energy sources in the galactic plane. So the GPS is really geared toward point sources and some diffuse emission, which is maybe associated with Fermi bubbles, but it is a hot gas primarily. So there is another important kind of sources in the galactic plane, which are the high energy extended sources associated with relativistic outflows with non-thermal particles that are actually ultra-relativistic. And so the question one can ask is actually what will we see those in GPS and what needs to be done to actually study those objects with axis, because axis is designed perfectly for studying this kind of objects thanks to sensitivity and high angular resolution. This is on the top, the area that will be covered by GPS. The very top is Chandra coverage, and actually Arash showed something like that with regions previously, and the second panel from the top is XMM coverage, and it does include some very interesting objects that will be observed by GPS, and we will get substantial number of photons there, but these objects have been studied by Chandra, some of them with quite long exposures, so the GPS still probably for some of these objects will produce better data than exist, but on the other hand, people did target those objects. Now the GPS will probably discover some new extended objects like these in the areas that are not covered by current pointings with Chandra and XMM, and this is really, important and interesting. But because the GPS exposures are necessarily shallow, otherwise we would need much more time than 3.6 megaseconds, right? we cannot really extract a lot of science for some of these objects compared to a deeper X observation. And I'm going to argue that for some of these objects, actually deep X-ray, deep X observations would be something that is very interesting. This is like just some examples of these extended high energy objects, such as pulsar wind nebulae. And this is a very exciting one because there's something which we don't understand happening here. It is injection of particles, very high energy, Lorentz factors of 10 to the 9, right? Very high energy particles into ISM. That's that sideways outflow, we call it. And high quality image, and this is Chandra, is really instrumental in understanding the physics behind the particle escape from the confined outflow, which you see behind the pulsar here by the bow shock, right? So this is something, one object that's very interesting. I think it could be a key for X's science. But there's other pulsar wind nebulae where actually I want to demonstrate here another property that X's can do is the spectral maps, right? Because it is a high resolution images, but there's also energy information for each photon. Well, the spectral maps for pulsar wind nebulae, they actually do allow to compare data and models of particle transport. That's what you really want. And with Chandra, we are only able to do this for very nearby pulsar wind nebulae like Vela and Crab. On the right-hand side, you can see fainter pulsar wind nebulae, where Chandra is really, even with 300 kilosecond exposure, cannot really do a good quality spectral map. There's a lot of fluctuations here on the right-hand side spectral maps, and here are the images corresponding to the spectral map. Right, so something like 100 kilosecond, 150 kilosecond exposures with X's for these kind of objects will do a lot better, and we will be able to see spectral evolution of particle SED. Another kind of objects that are called relic pulsar wind nebulae or plerions, or sometimes TeV halos, we are not really able to study them efficiently in X-rays now because they're very faint, right? There's actually kind of like cooled population of these relativistic particles. They still produce X-ray emission. You can see this in XMM. So on the top this is TeV source, very extended, famous TeV source, J1826. Lots of papers written about it. And actually now, these are Hess images, but now there is this Hasse collaboration which detects these sources up to hundreds of TeV, which is very interesting, I think. And so to understand the relation between the pulsar that happens to be within this area, but it is offset from the center of TeV source, one needs an X-ray, for example, image which shows the more compact X-ray nebula, which is bright near the pulsar, but then it extends toward the center of the TeV source. This is the small square is what is shown here. Right, it's a very faint in X-rays, requires long exposures. XMM background is typically too high, ACEs, Chandra is field of view too small and effective area too small. So X's will be really helpful in studying these sources. Moreover, there is now deeper radio surveys that will actually hopefully discover these electrons, relativistic electrons in radio. And so to connect radio and TeV from CTA and SKA, for example, X's would be a very useful bridge between those. Okay, and so that's like going to answer interesting questions about particle transports and such as like a positron excess that is observed near the Earth and so on. So there's something very interesting that X's can do, which is really difficult to do now with Chandra and XMM. It's seeing magnetar wind nebulae. So magnetars are bright in outbursts, but when some of them are actually very dim when they are not in outbursts. This is an image of a magnetar which was not known. There's just like really faint extended emission here, which is something like 3 sigma maybe detection. When the magnetar goes into outburst, and then it disappears, but the emission, this faint emission remains, it just becomes a bit brighter. And so finding things like those, which actually point to quiescent magnetars, is something that X's can do. And I think these magnetar wind nebulae are actually intrinsically maybe faint, because there's another example of magnetar wind nebula in the supernova remnant, where we thought this is a pulsar with somehow strangely very faint pulsar wind nebula, but then it went into outburst and it turned out to be actually a magnetar. So there's a lot of interesting science there. And to finish up, there is an interesting connection that one can study with axis between the supernova explosions, the types of compact objects they produce, and the actual mechanisms of supernova explosions and progenitor stars, right? Because everything starts with progenitor star, but we typically do not know what it is. But we can kind of do this fossil record exploration of the supernova and the compact object to try to actually understand what was the progenitor star and how the explosion happened. And pieces of this puzzle are neutron star kicks, like how fast they move. Some of them move very fast, like this one I showed before, Lighthouse Nebula, moved out of the supernova remnant, and some they stay in the center. Some of them have pulsar wind nebulae in blue here, and some of them do not have any pulsar wind. This is called CCOs, is a different type of neutron star. At the bottom, we have magnetars, I mentioned before. And so there is this pieces of puzzle which we can really put together with axis thanks to the big viewing area and sensitivity and actually ability to measure spectra, like and see spectral lines and measure abundances from supernova remnants. And so the pieces are here, like how different are neutron stars in terms of having, not having pulsar wind nebula, how different are actually abundances in the spectra of supernova remnants. And this is all can be actually studied effectively in single observation with axis. And here is another example of this connection. For example, neutron stars seem to be neutron star direction of motion seems to be associated with asymmetries in some of the supernova remnants. And these asymmetries can be not only in the emission, they can be just in the distribution of abundances. And here's my summary slide, which basically just to summarize the two main points, that axis will produce a lot of new sources, point sources. It will detect, they will be detected in the axis GPS, but we do need certain things to be able to make effective use of those numerous X-ray sources. And also there is this other part of science, which is extended high energy objects, where deeper observation with axis may be needed, although some of these new objects of that type will be discovered in GPS. Thank you very much. I'm done.
Thank you, Oleg. You may also assume tremendous applause. I'm happy to take any questions from anyone. I see Mike, I see your hand up. Do you have a question?
Yeah, really nice talk. That was really interesting. So thinking back to your sort of first part when you're talking about the difficulty classifying different sources, I was thinking about with the extremely large telescopes coming online, there'll be very high resolutions. So I guess that'll give you much better ideas about sort of what what the infrared emission is. So do you think that will help resolve a lot of figuring out where these X-ray sources would be?
It's a kind of double-edged sword. So first of all, of course, multi-wavelength information is needed to do effective classifications of faint X-ray sources that have only, say, 100 X-ray photons or 20 or something. And those will be really most of the sources in the GPS, as Arash showed by the luminosity function. So multi-wavelength information is needed. So, but again, if you go and obtain a deep near-infrared image, the thing is that you get too many possible counterparts. And what needs to be done really there is one has to consider all possible counterparts. They will have different probabilities of being associated with X-ray source and do the classification. Once you get out the classifications, they are weighted with those probabilities of being associated with a particular near-infrared source. And then you can make a judgment on the ultimate class of X-ray source. So I would say that yes, those deep near-infrared data with high resolution are actually, in the end, better than not having them. Yeah.
Okay. Chris, did you have a question?
Yeah, thanks. Well, actually, one comment and then a question. So the quick comment, and especially I say this because there may be people on the call who have not really followed the programmatics very well of probes or of axis, is and this follows very nicely from Oleg's talk. The 70% of the observing time of axis is open to guest observers. It's open. We're in very important way. We're building a community facility here that will be open for anybody to use, and that actually includes science team members. Science team members can actually write geo proposals as well. So I think you highlighted an incredibly large number of exciting topics I could imagine could form the basis of a lot of these different follow-up investigations. I think the Galactic Plane survey will be this incredible discovery machine for things that can be followed up by the community, by guest observers. So I think this is really fantastic. My question is actually related to, and this sort of bridges both talks here. I mean, these filaments that we're seeing in many different wave bands are very interesting for those of us who like magnetic fields. So in the galactic plane, or the galactic center region, there's these incredible meerkat filaments. What do we expect them to look like in the X-ray? I mean, I've stared at Chandra images and I don't see them in the Chandra images, but is there expectations that if we have more sensitive data, we'll start to see X-ray emission from those radio emitting filaments, and is there an interesting physics there to learn?
Arash, would you like to go first, or would you like me to try to first answer?
Go ahead. I'm going to try to think of an answer as you speak.
Okay, so yeah, people, as I said, very interesting question, actually. In fact, people did look for X-ray counterparts within the galactic center region to those radio filaments. They find counterparts for several of them. Whether it is actually just like a different subset of those filaments that have X-ray counterparts and the rest don't have counterparts, it's not clear yet. One type of object here that one could think would have maybe, but it's not, we do not detect counterpart of this outflow in the radio yet, but it may be because the radio images are not deep enough, is this kind of filamentary, if you like, outflow that we see in X-ray from this lighthouse nebula. In fact, some theory papers were written by, I think, Maxim Lutikov and some others about those filaments in the galactic center region, that they may be associated with the pulsars, actually, systems like this. But I would not bet my life on this yet. Maybe it's not. Yeah. In the rest of the galactic plane, I think these are really prominent to the center of the galactic plane, but really I don't have access to a meerkat, let's say, survey of the galactic plane images. So it may be that there are some more of these filaments. I don't know.
Okay, thanks.
Arash, did you want to add anything? You don't have to, but.
Not necessarily. No, I don't. I do want to look at that, though. That's the next thing to do, is to use the meerkat. Given the meerkat image, I was only given that or made aware of it just two weeks ago. But we could use that meerkat image as the input for the diffuse emission simulation. And I'd like to see what Axis would find. But I need to know the energetics, the spectra of that thing, those filaments. Oh, one more thing. NuSTAR has seen some of those filaments, but I'm not sure that the same filaments that we're seeing in the meerkat image. So there are some hard X-ray filaments seen by the NuSTAR telescope that were not seen by Chandra necessarily. And I would say that Shua Zhang and collaborators should be the people to ask on that question.
No, thanks.
Okay, thanks. Are there any other questions? If not, Mike or Chris, did either of you have anything you wanted to say at the end? Nope.
I'd just like to say thanks for two really interesting talks. I think I'm very excited 10 years from now to see what these data look like. So